Alright, start. I don't have the camera, I don't have the Canon, so I just going and use my iPad and see what happened here. And yeah, so it's just one long 30-minute video on January 2018. So much people was asking for that. So I really have nothing else to say. Oh yeah, in the clip I messed up. I said something about the scale. I said the wrong scale. Just watch the scale that I have there, but everything else is cool. So, and I didn't really do solutions for all the questions, but I guided you through so that you'll be able to get the solutions once you're revising for every single question. So, blessings. Alright, no camera, but the physics must go on because I have physics tomorrow. So I'll just record it straight off my iPad and just upload it, and hopefully it bless somebody's heart. This paper is Jan 2018. Most requested, about I must see 100 requests on this between my Instagram, my email, and my people sending me on different thing on this paper. Alright, so we're going to do the whole paper, and I'm going to have answers for everyone. I will guide you how to do everyone because I just like whip this out and squeeze in some time to do this. So this will be a quick video before I get on to some other things. Alright, so a student conducted, blah, 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 blah. You find sign R, you find sign I in this. By the way, you need to do the paper first, right? So this will only help people who familiar with the paper, or if you have the paper and you're just running it through and stuff like that. Okay, complete the table. So let's calculate. I think you get 5 marks there. A lot of marks will pass in this question very easily. Plot a graph of sine R against sine I. Now the chances of this coming back in June is very slim, but it may come back in a different question. Anyhow, say plot your graph. I just do up this graph quick. I didn't finish the scale. The scale is 2 centimeters to 1, 2 centimeters to 1 to what 0.5. 2 centimeters represents 0.5 on both axes. So x-axis. Well, you need to put in a scale. You need to put in a title. You need to label up whatever. That's the proper thing to do. Then calculate the gradient. Just use 2 points on the graph now. When you're calculating the gradient, make sure you use a point like about here and a point like about there. None of the points real close to each other, and it must be a point on the graph, not one of the experiment points unless it's on the graph. So you could only use a point that's actually on the line on the graph. Don't use a point like off the line. So use that gradient. State the name of the physical property represented by the gradient. This is state, so you can just write is the refractive index. But there's a little tie-up thing in this question, because watch. It's really sine R over sine I. So that is sine R over sine I. If you look at the gradient, that will be not the refractive index. That will be, because this is refractive index, the gradient is sine R over sine I. By the way, my son just singing the alphabet over and over and over in the background. Anyhow, so yeah, what I'm saying is that this is the gradient, but this is the refractive index. But then you need to realize from the start of the question, he was going the opposite direction. He was going from glass to air. So R here is really I, and I here is really R if he was going this direction. So the gradient, since it's inverted, the gradient will be, I just need to go back and take off that. My OCD acting up there. Yeah, so it will be, what I want to say, it's just going to be the refractive index of glass to air. No, glass from air to glass, right? So normal refractive index thing there. Woman being, explain the term critical angle. Alright, there's a definition from your book. Critical angle is the angle of incidence that gives the angle of refraction of 90 degrees. Yeah, check over that. Anyhow, so using table 1, otherwise state the critical angle for the glass, blah 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 blah. Alright, so you're just going to state your gradient. That's the critical angle. This is state, no major calculation. State means just write down, right? If the refractive index from the cladding to the core is 1.03, calculate the critical angle. Yeah, so you're just going to use this relationship where n here represents the refractive index. Refractive index is 1 over sine c. Substitute, see what you get, put your answers in the comments. Later tonight, like around 11 o'clock, I'll pass through the comments and take a look at all the answers, drop in some comments, some recommendations, ting. Who knows, I may just do this topic that people are asking for to logic gates. So you'll just check the channel in the morning to see if you see a quick video on logic gates. If I don't get it in, it's because I just didn't get the time to fit it in when I get a chance later tonight. Anyhow, so complete table 2 to distinguish. Okay, this is just some real easy things, so just fill in this. They actually give you the words to use. Some of these words might repeat. So You just put it in inside here now, but use your book if you don't know this. If you don't know this at this very late hour, take a belt and beat yourself. So students in a 5th form class, so okay, let's go to the next page. So yeah, you're doing some specific latent, no, not specific, yeah, specific latent heat. So next page, you had to work out, convert time into seconds, minutes into seconds. So you had 5 minutes 45 seconds. That is our next kind of easy thing. So you work out that for yourself. Then calculate the mass of water evaporated. Well, you start off with this mass and then you end up with this mass. So what did I do? I erased the whole thing. Yes. All right. So yeah. So this going to give you that. I do all the easy questions and see performance here. All right. So the power of the electric heater was this. Alright, so you need to a lot of physics is just pushing things in equations, and sometimes if it's like plenty marks, you have to put it in one equation, get something, and then put it in the next equation, and that's exactly what you have to do here. Alright, yeah, just get interrupted. I'm back. So power is equal to the rate of doing work, and yeah, what I'm saying here is that work done is really energy, so I just use this formula. You could use whatever. Power is basically work done over time taken. So if you want to find energy, which is like work done, you multiply the power by the time. Make sure all the units work out. Yeah, they give you watts, so that's nice. There's the SI unit there. So what is the time? The time is what you work out here in seconds. Whatever answer you get there. That will be your energy, and then you're going to take that energy and put it into a specific latent heat equation. Make sure you put on a good performance there. You already know the mass as well, which is 15. That's a nice answer. And you'll be able to find your latent heat of vaporization of water. I forget what that numbers are wrong. What that numbers are wrong, but if I see the answer, I'll be able to know whether it's okay. Anyway, define the term energy and state its SI. Easy thing. Go and learn up the definition. State its units. Energy is really the ability to do work as a. Yeah, energy is like a scalar quantitative quantity that body possesses that gives it the ability to do work. Something like that you'll write down. Go and check your definition in textbook. This is just based on what I have in my mind. Complete main form of energy. Okay, the easy thing again, radioactive decay. What type of energy? Radioactive energy. Radio waves, X-waves, electromagnetic energy, objects in motion, kinetic energy. Alright, so go and check all the different types. Make sure you know that down. Say the main energy conversion, flashlight. Alright, so you have the battery, so that is chemical to electric to light energy. Alright, so your state diagram marks to that you just need to state. So yeah, that sounds good. And then let me just take back all that. Right, and then calculate the maximum kinetic energy pendulum. This is a popular question. Go and check out. By the way, all the experiments in your physics book, once you have a good quality physics book, all the experiments, make sure and check them out. And you're familiar with them and you're able to see how they're going. And yeah, make sure them is like your friends and things. So yeah, so what happening here is that we want the kinetic energy of the pendulum. So you're just going to plug in the maximum value for V here. You already have the mass. They give you a mass. Yeah, mass. Everything looking in SI units, good. So you're not in units. So just plug it in the kinetic energy equation. Half mv squared. Then, so you get 3 marks again for that. Use the principle of conservation of energy to find maximum. So you're just going to say that whatever answer you get here in the last part is the same as what answer you get here, and then you're stating the principle of conservation of energy. Energy cannot be created or destroyed, it's converted from one form to the other. And you need to parallel assumption to that all the energy from the kinetic is being transformed into the potential energy. So that's about it. And right, can't create energy, you can't destroy energy, you could only convert it from one form to the next. And the base form that everybody end up in is heat. Calculate the greatest height. Alright, excuse the screaming in the background. Calculate the greatest height, H, right? So you're using the formula for potential energy, mgh, right? Mass by gravity by height, acceleration due to gravity by height. Yeah, so equal mv squared, well, half mv. No, actually, you're done already. We call the energy, bro. You have the energy from the force. So you just plug in that value, plug in g, plug in M, get H. That is physics, and just one formula into the next formula into the next formula. So yeah, that is your PE formula. Go and learn all your formulas for energy. Arguments 1 against nuclear fission. Arguments 4. What is good for why nuclear fission is good, boy? Because efficiency is just all the way up. For like the same mass compared, the same mass of fuel when compared to like coal or natural gas is just way superior. What's the next reason for nuclear fission, boy? Next reason, no greenhouse gases. No greenhouse gases. So no greenhouse gases like carbon monoxide, carbon dioxide. And this one was efficiency is just nice. So the amount of energy you're getting per mass is superior. Arguments against, well, you could come up with plenty. Radioactive waste, that's the first, radioactive. Earlier, just spell radioactive there. Radioactive waste and radioactive fallout. Right? If the plant melt down and thing, you have a little Chernobyl disaster scene could take place there. Yeah, it have plenty things against nuclear. There are plenty, but there's some scary things against nuclear. You know what Fukushima nuclear disaster to happen where thing leaking into the sea and all kind of thing. Alright, so yeah, nuclear fusion is seen. Fusion is the good one. Fission is the bad one. Fusion is where the two things come together and say boom, you're gonna make a new. That's just awesome, right? Like a new element. Two atoms come together and fuse. Just insane stuff is just be happening. Alright, so nuclear fusion, we ain't really had this down cork now. We can't really produce this good yet. State two advantages of the nuclear fusion over nuclear fission. Well, we don't have no radioactive waste to deal with. And you would need to worry about no nuclear fallout. You do, and the fuel is a deuterium or is a type of hydrogen, an isotope of hydrogen, I think. The fuel cheap. Yeah, easy to get that. All right. So what next? Correctly complete the following nuclear fission reaction. Only what you say. 2 plus 2 is 4. No, well, okay, I already know. 2 plus 2 is 4. Minus 1, that's 3. Quick maths. Boom. Alright, so yeah. That's that. So you complete that equation there like a boss. I don't know what these lines are about though. Maybe it's to do the calculation. This is not supposed to be here, right? You just put that there. So yeah, so you just complete up that. This is your mass numbers, this is your proton number, your atomic number. Ding 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 ding. Next part of this question. When they do this, they're about to hit you this equal mc squared Einstein equation about to come into play when you see this kind of table and your mass, atomic units, blah 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 blah. Alright, so you have your mass, you see how tiny them numbers is because that's the actual mass of one atom of that. Anyhow, so they're going to ask you to, yes, calculate the energy released in this reaction. So here you're doing this, add up the two masses. So they actually give you, sometimes they give the mass of like a neutron and proton, and you need to go and work out how much neutrons and proton and add them up and ding. But alright, so you have the full thing given to you here. So this is the mass of your reactants. You see what's going on with my handwriting? Reactants. And then you have the mass of your product here, right? Product. But this writing with your finger thing is problems. Yeah, so my handwriting a little better than this in real life. So anyhow, so you have your products on this side, you have reactants there. What will happen? What's just this cool thing that happens in these kind of fusion and fission and thing? The mass of the product is going to be a tiny bit less than the mass of the reactant. So you need to subtract and you'll get a difference. That difference is going to go into the almighty formula equal mc squared. Well, God is almighty, but this formula good mighty too, right? It have plenty mightiness. Alright, so you're gonna put in that M, and the M gonna be the difference in mass that you lost here, right? And that difference is going to multiply by the speed of light squared, and you're going to be able to calculate the energy. It's going to be a tiny amount of energy because you're only dealing with one, but when you multiply that from an atomic scale to a real life scale, it's plenty energy. You could just ask Nagasaki and Hiroshima and them boys about that. Anyhow, so newtons and huge, I'm not going to do this. This is only textbook thing. Go and find that in your textbook. A homemade projector is constructed. I don't mean to sound bad, but yeah, for 4 marks, you could read your textbook on that, right? So or you could research it on YouTube right here. A homemade projector suggests with a reason an appropriate distance from the lens at which you phone to get a magnified image. Alright, so if it's a magnifying glass, it's convex lens. So you would want to put it between F and 2F, between F and 2F. F is the focal length and 2F. So all them ray diagrams with your convex lens, and you have your F here, and then you have your 2F here, and then you go on, so an F and 2F here on your principal axis, and then you have your whatever. So yeah, so and then you want to put them here, so you will magnify somewhere beyond 2F there. So make sure you know all them diagrams, and when they ask a reason, I will just hit them the diagram on the side and call that George and explain that diagram a little bit to them, right? So check over all the diagrams. This question is asking you on one of the diagrams. There are quite a few. Check them over. Here what to do: draw each one over. It will only take you like about 20 minutes. Draw each one over. Make sure you could explain it a little bit, and you should be good. If a phone is placed, okay, there's always asked these kind of questions with this question. I remember it as if it were yesterday. 1 over u plus 1 over v equal 1 over f. That's the formula you want to use. What they're asking you for. Calculate what? Calculate the distance, the screen. So that's the object distance, the image distance. It doesn't matter because this is what you call this commutative. So whichever one you let be whatever, you'll still get the answer. So you plug in your image, you plug in your object distance, your image distance, and your focal length, and you'll be able to solve it using that once your mathematical skills reasonable. Alright, calculate the magnification. Magnification is V over U. Yeah, this equation setup is not commutative, so this has to be an image. Yeah, I hope I remember that correctly. This has to be an image, this has to be an object distance, and I'm in a position to check things with my textbook right now. So image, object, and you substitute. And what we're looking for, magnification of the image on the external screen. So, oh shucks, we're looking for the magnification. I kind of zone out there. So right, just plug in this, plug in that. We got this from before, we got that from before, and you get the magnification. Right, cool. You just use that formula. By the way, all the answers, put it in the comments. Let me see, and I'll pass through and I'll check it later tonight, hopefully. If the dimensions on the phone and this, okay, you just use the magnification. Like I said, the magnification was 1.5, then this will be 11 by 1.5, whatever that is. 6 by 1.5 is 9. Yeah, get something like that. But I don't know what the magnification is. So I have to find out what that is. And you just multiply it and get new dimensions. 1 mark. State whether the image formed it's inverted. Once you do your diagrams, thing like what I tell you, you'll know all that. You need to know how to describe the image: inverted, upright, real, laterally inverted. All them things now. Diminish or magnified. But convex lens, the convex lens, which is like this, the image is you're always gonna get inverted image. Concave, I think you're always gonna get a upright image. Let's move on. So yes, so this is the question a lot of people will be asking in the comments as well. Not a lot, but a noticeable amount of people were asking in comments about Fleming's right hand rule and Fleming's left hand rule. Right, the Fleming's left hand rule is for the motor. So that is when you want movement and thing of the coil, you want to use the left hand rule. I just think of it. I don't know why I remember that because motor is the first one in my textbook when I learned it. 11, 12 years ago, more than that. So I just remember that. And then the AC, the generating one, you want to learn the right hand rule. This question is on the left hand rule, I think. So, well, this part of the question is not even on that. This is just a magnetic field. So complete the following diagrams to show the magnetic field of the current. Oh, that next piece of the question on this side, right? So where the current is directed into the paper. So this has nothing to do with the magnets I was showing you before. So what you want to use is the right hand grip. The right hand grip is your thumb pointing up, then you have your hand and the fingers. What's going on with them fingers, buddy? Alright, so yeah, there's this man's fingers here, but your thumb is where it's going? Into the paper. So you need to point your thumb into the paper and you'll realize that how it's going to go, boy. It's going to go like this. Ooh. Parallel arrows on them there to indicate now, boy. Yes, so and you maybe draw about 2 more and call that George. Yeah, I would have draw 3. Nah, I would have draw 4. Alright, so the resulting magnetic field when the current carrying conductor is placed between the poles of the magnet as shown in figure 6. Alright, so you start off with your circles first, or you start off in this kind of question. By the way, there are a few diagrams like this you need to know. You need to know your electromagnet and your solenoid and how these wires will look in the field going in and out. Drawing these circles is a nightmare, boy, especially when I'm doing it live, so I can like edit and pick a best one that I do. I'll just pretend these circles looking beautiful, you know. So yeah, use your imagination. So what I would do when I do this, remember this was going like this. We're using the right hand grip or the Maxwell screw, some Maxwell screw thing it up. But I use the right hand grip. The right hand grip is the nice ones for this, for the wire now, to know how the thing. So you're starting off here. You're going and go. What will happen here? When he's going here, he will see his boys them rolling. So he will get influenced. Bad company, boy, bad company. So he will start to follow the flow of them. But make sure he come back in. You notice his length come back in the same spot there. Yeah, let him come back so the field of that magnet getting bent up, and then this one would go so. Let him kind of squeeze in, and let this one squeeze in. So what happens is you have a high density here. Maybe you could draw a last one on top. That good. And on the underneath, just draw one. One is good. And a little low down. He wasn't influenced. He followed his own direction and he make it in life, right? But all the rest get influenced. But even the ones that start low here would get disrupted. But I don't go into all of that. So just this should be able to get 3 marks. What I want. Yeah, I feel like good enough. So make sure you put in your arrows and thing. I will call that George. You can just check it over in your textbook in case I'm leaving out anything. Right, so this is the part that's really interesting. Name the part labeled X, and I believe a lot of students are introduced to this in a kind of shady way that they never really understand it, or they never really pay attention to it, because people are always complaining about this. Name the part labeled X. This is a commutator. That's this part, right? Commutator, split ring, commutator. The purpose of the commutator, they could ask that. I don't think they asked that here. No, they didn't. They could ask that is that's to make sure that the current keep going in a nice favorable way. It switches the direction of the current. One moment it going so, and the next moment it will be going like this. So and that will allow the field to be the polarity of the coil, which is this thing here. This is called the coil, to be flipping. One way then the next way, one way then the next way. That will mean every time it make a half turn, it going and flip, bam, and then flip again, and then flip again, which means that the movement will always be going in a proper direction. If it didn't use to flip, what will happen is when this coil reaches the top, it will swing back down. It will kind of just be fidgeting between itself like this, and also it will mean that this wire would have to be connected to here and connected to here. So it wouldn't spin properly. It wouldn't spin properly. The wire will knot up. Or if it had one continuous disc, it will just be oscillating backward and forward like that, right? So there's a real nice video on this. There's lots of videos on this on YouTube. You can just go and check them out. Check this one out. DC motor rule or split ring commutator. Hopefully you could get an epiphany like this guy. This video kind of shows nicely how it's done. Make sure and watch the end of the video, like around here, so it's the sweet spot. And you can check it out before your exam, and now you'll have something in your mind to see. A lot of these you want to look for little 3D animations. Sometimes you don't want to look for the live actual thing, because it may be hard to see. They look for little 3D animations of it and let yourself feel good about it now. So yeah, okay, enough talk about that. Commutator. I didn't even finish Bollywood. I just started to talk. Alright, so yeah, explain what happens when the switch is closed. Your answer should include the direction of the current, the forces acting, any rules apply, the direction of rotation, and how continuous. Lord. And then they hit you on 9 marks. These kind of questions is just 9 marks, and yeah, these kind of questions is just hot up people. Now let me tell you, as I said in the previous video, when they say 9 marks and they do these things, I will give them everything. I will write down everything. I will hit them 3 diagrams. I'll hit them the 3 diagrams. The one when it's like this, the one when it's 180 degrees, and the one when it's on the next direction. Don't forget to label your parts. I think this was DCBA. I will also hit them the Fleming's right hand rule on this side, and I will show them how Fleming right hand rule works, with the thumb going for movement and the index going for feel, and the middle finger going for what, current. Yeah, I would show them, I would explain how that works on that side. Just make sure you don't draw any margin that they say don't draw in these kind of paper, because when they're scanning it, that mightn't come true and you'll just not get any marks for that, right? So yeah, so if you read through this, it kind of scrappily done, but let me just say the key points on this. This is what happens, and as I say, check out this video, go in your textbook and read it through. Make sure you kind of at least grasp a okay understanding of it, where you could regurgitate it for the exam. But if you could understand it fully, best. Physics is the thing. Physics is not a subject you could really wing by just doing past papers alone. You need to understand, and that is what beats people out sometimes. Anyway, enough talk. Creates magnetic field around the coil when you turn on the switch. So this activates the field, and the same field according to the grip rule. And that field opposes the magnet's field based on the position. It causes DC to move downward according to Fleming's right. Did I say right hand? I should be saying left hand. If I say right hand before, I'm supposed to be saying left hand. Alright, I can edit it. So an AB to move upward. So you need to check out what I'm talking about here. So this will go this way, this will go this way. No. Let's just check this. Current is going, so current is coming here. Current is going this way. Point your finger in the direction of the current as the middle finger. The movement and north and south. Okay, the movement is downwards. If you set up your finger properly, just do this. Point your finger. Point your finger. Point your finger. So, alright. Point your finger. This finger is the current, so that's the middle finger. Then point your the finger that you feel, or it's called like index finger, that way, and wherever direction your thumb facing, once you set them up good, it should be facing down like that. So I was wrong. So yeah, we look at DC move downward there. Why I draw the wrong thing on the diagram? So DC would move downward, this one will move upward, and it will spin for until it reach 180 degrees. At 90 degrees to the position, I kind of state this a little vague. Maybe I should have said a half cycle. Causes the circuit to break. The coil, not the coil, the commutator. Causes the circuit to break. So commutator. Momentum carries the coil over because it's spinning, so it will just spin over. Even though it breaks, it will spin over. And this reconnects the circuit on the commutator. Essentially, this prevents the direction of the movement from flipping every half cycle by maintaining a favorable polarity in the coil. So in the beginning, the current flows like this, DCBA. Then the commutator switches the current flow to ABCD. Let me look at that. Imagine if this whole thing flip over now. This is A, B. So it'll be going A, B, because the current going in the same direction thanks to them commutators, you know? So it switches the direction of the current in the coil, but it go in the same direction in terms of space, which means again the same downward movement here, and again a downward movement here, but an upward movement there. This is 29 minutes. I need to stop. Anyhow, so yeah, that movement is a couple that causes rotation. This means using Fleming's left-hand rule, the direction of rotation is continuous and in one direction. So just to make sure I hit all the points that the examiner has been asked to look for, I would draw the diagrams, really explain what I know about it, use proper English, and write Fleming's rule, make sure I touch all these points that I said, direction of current forces acting and rules apply, blah 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 blah, and that's it. Alright, so I think this may be the last I'm able to do for the night. I was trying to make this video in 10 minutes and go to 30, and I will pass back in later when I get the chance and look at some of your comments. Sorry you couldn't see my face. I know some of you will be missing my face. Let me just draw this. Later, fellas and ladies, that's my birthday. So all you do good in all your exam, right? Blessings.